or false, the A in the equation AX equals B is an augmented matrix? False. It's just the coefficient matrix. Yep. The augmented matrix, to answer your question, Rich, the augmented matrix is when you put the B is the thing, is a vector of the things on the other side of the system of equations. It's when you augment means to add, so you add that to the coefficient matrix. Yeah. What's the name of this matrix 1001? Identity. I'll take identity. I'll also take I sub 2 for the 2 by 2 identity matrix. Okay. You'd have to write 2 by 2 identity. No, it's not. It's not a Jacobian matrix. No. Okay. True or false? A matrix equation, a vector equation, and a system of linear equations are all equivalent ways to express the same thing. True. All right. Don't forget to record your score in your folder. All right, so just a little reminder where we're at. We're going to cover 1-4 today, 1-5 Wednesday, and Friday you have your first quiz. So I want to point out that it does cover material from the previous class, like there's no lag. But the first half of your quiz period is going to be spent on a group quiz where you can discuss with everyone, you can discuss with me. So if there's still remaining questions from 1.5, like that's sort of your opportunity to get those answered. And then the second half of class will be an individual quiz. Your grade is going to be like the average of your two, the group and the individual. Okay, so today we're going to learn even more notation to represent a system of linear equations. So we have the augmented matrix that we learned the very first class. We have vector equations that we learned last class. And today we're going to use another new notation. And we're also going to be able to tell if a set of m by 1 vectors or if the columns of an m by n matrix span a space. All right, so consider this system of equations. 3x1 plus 2x2 plus 7x3 equals 5, and x1 minus x2 plus x3 equals 8. So we've got three unknowns, just two equations. I want to write it as a vector equation. Okay, so my vector equation, how do I do that? Somebody remind me. Yes?
Start off with x1 and then put in brackets 3 over.
Yes. So I put my 3, 1 is my vector, and then I put x1 like as a weight. All right, and then I'm going to do a similar thing for x2 and x3. So for x2, I put 2 and -1, the coefficients on x2, and an x2. And for x3, I have 7 and 1, x3, and I ran out of room, so I'm just going to write down here, equals the vector 5, 8. Nope, it does not matter. You could put x1 and then the vector. It's multiplication, so it's commutative. Yeah. All right, if I want to write this thing as a matrix equation, I gather up my three vectors, my three coefficient vectors, and I put them together into a coefficient matrix. All right, so my matrix is going to be 3, 1, 2, -1, 7, 1. And then I have a vector of my unknowns, which means that's going to be a little bit longer. So then I've got a vector of unknowns, x1, x2, x3. And that should equal 5, 8. So we're going to talk about matrix multiplication in a few minutes and how these things are equivalent, but that's the translation. Augmented matrix, that's where you write the coefficient matrix, 3, 1, 2, -1, 7, 1, augmented with the other side of the equal sign, 5, 8. So regardless of what form I give this to you in, how would you solve this system of equations? Row reduce the augmented matrix. All right, so remember from the reading that the product of an m by n matrix A and an n by 1 vector x produces an m by 1 vector A times x, AX. So it's the linear combination of the columns of A using the corresponding entries in X as weights. So let's practice. We're going to do it kind of two ways. We've got the book's way of thinking in terms of linear combinations with weights from the vector. And then I'm going to do it another way that I don't know, some people like better. I like the other way better, but they're equivalent. They're totally the same. Okay, so linear combination of the columns of A using the entries in X as weights. So this is A, this is X. So I take each column of A, 1, -3, 1, and I use a weight, the corresponding weight from the entry of X. So this one's going to get a -2. And then I'm going to add, because that's what a linear combination is, the other column of A, 2, 1, 6, times my scalar 3. So my final product here is going to be -2 plus 6, which is 4. Yes, the vector is -2, 3. This whole thing is a vector x. Each individual entry of a vector or a matrix is a scalar. So that's 6 plus 3 is 9, and then -2 plus 18 is 16. 9, 16. So that's how you multiply a matrix times a vector. Each column of the matrix, take a linear combination of those columns using the weights in the vector, using the entries in the vector as the weights. Yeah, the number of entries in your vector has to equal the number of columns in your matrix, otherwise this is impossible, right? You have to have the same number of entries as columns so that you can put one entry as a weight on each column. Okay, I'm going to do it one other way. You don't have to copy it down if you don't want to. Let me just get a new page here. Okay, so I think of multiplying each row times each column, right? So I only have one column in my second factor. So I'm going to work row by row. I'm going to take the first row and imagine that you could like pick it up and pull it out from the board, turn it 90 degrees on its side, and lay it down on top of the vector. The entries that match up are going to get multiplied together, and then you add the results. So first of all, I need to know how big my answer is going to be. What are the dimensions of this first matrix? 3 by 2, right? And I'm multiplying that by, what are the dimensions of that vector? 2 by 1, right? So this is how a quick check to make sure you can multiply things together is that the inner dimensions have to match, okay? Inner dimensions have to match. And the answer is going to be the outer dimensions. My answer is going to be a 3 by 1. Okay, so I'm going to make room for 1, 2, 3, a 3 by 1 matrix. Okay, so now go back to take that first row, turn it 90 degrees, put it on top of the matrix. And the things that line up, you multiply. So I've got 1 times -2 plus 2 times 3. And then you do that with the second row. So second row times of the first matrix times the first column gives you the second row, first column of your answer. So turn that 90 degrees, and we have -3 times -2 plus 1 times 3. And then do it with the third row. 1 times -2 plus 6 times 3. And this should come out to 4, 9, 16. Same thing we got with the other method. The two methods are equivalent, and you can use whichever one makes sense to you. All right, let's look at part B here. I have a matrix, a 3 by 3 matrix, right? This is 3 by 3. I'm multiplying it by a 3 by 1 vector. Can I multiply them together? Yes, the inner dimensions match. What's my result going to look like? 3 by 1 vector. Good. All right, so I'm going to do it this original method that I showed you. So I take each column of my matrix and multiply it by a weight from my vector. So I'm going to have 1, 1, -3 times x1 plus 3, 5, 7 times x2 plus -4, 2, 6 times x3. It's a different system. Okay. So you can see how a matrix equation, right, where you have a matrix times a vector, is equivalent to a vector equation, right? So this, I don't have an equal sign, but this would be like the left-hand side of a vector equation. Yes.
Yeah, it seems like we're just like kind of like both these first.
We are.
We started off like.
Yep. Yep. I've taught you 4 different ways now of representing a system of linear equations. And part of what we're doing in the first part of this class is just learning how to like easily translate from one to the other, because in some situations when things get more complicated, some of these notations will lend themselves better to the kinds of problems that we do than others will. Depends on what you're doing. Nope. Nope. All right, here are many questions that all mean the same thing. We looked at the first 3 of these questions last class, right? We already discussed what these 3 questions mean, that they're the same thing. Is a vector a linear combination of 2 other vectors, right? Is the same thing as asking, is the vector 4, 12, 4 in the span of those 2 vectors? Because remember, the span of a set of vectors is the set of all linear combinations of those vectors. And then also, is that vector 4, 12, 4 contained in the same plane as the other 2 vectors? 3 ways of asking the same question. All right, here's a bunch more ways that I can ask that same question. Is there a solution to this system of linear equations? Is there a solution to this vector equation? Okay. Is there a solution to this matrix equation? Right? Is the vector 4, 12, 4 contained in the span of the columns of this matrix? That's the coefficient matrix. So instead of using the span of a set of vectors, we can think about the span of the columns of a matrix if you think of those columns as vectors themselves. Yes?
Is there any advantage at all to actually, when you want to, is there a solution to this matrix equation?
Given the fact that the vectors is x1 and x2, the column represent the x1 and x2 respectively. I mean, is there any like advantage writing it this way anyways?
Yes. Well, yes, sometimes there's an advantage. We will definitely see that sometimes there is a definite advantage to using the matrix equation. You can solve really, really fast, but it's going to take a little bit more development of theory to understand how and why.
Because from what I see so far, I think it's the exact same thing as S.
Of course, they're all exactly the same. They all say exactly the same thing. Yes. Yes. Yep. Is this vector a linear combination of the columns of the matrix? I could give you an augmented matrix and say, when you row reduce this, is it consistent? Yep. How do you solve how do you answer all of these questions?
I don't know.
Yes. I mean, not what is the answer? How do you get the answer?
Row reduction.
Row reduce the augmented matrix. No, sometimes you can tell without even augmenting it. If you row reduce just the coefficient matrix, you can sometimes tell if it's going to be consistent, but we'll talk about in a minute. Yeah. Yeah, sometimes you can't, sometimes you can. Row reduce the augmented matrix. Right now it's the master key, yeah. We're going to learn some other techniques as the semester goes along. Yeah. All right, if we let A be an m by n matrix, all the following statements are logically equivalent. So logically equivalent means if one is true, they are all true. If one is false, they are all false. So if I asked you any of these questions, right? Maybe I ask you, does the matrix equation AX equals B have a solution no matter what column vector in Rm you sub in for B? Like, that might be a hard question to answer. Instead, you could say, well, A has a pivot in every row. That's true, so this one's true, right? So if I ask you one of these 4 questions, sometimes it's easier to answer one of the other ones. And if you know the answer to another one, you know the answer to all of them. Okay, so these are, does the matrix equation AX equals B have a solution no matter what B you put in there, right? That's one question. Every column vector B can be expressed as a linear combination of the columns of A. Equivalent question. Or equivalent statement. The columns of A span Rm. That means that the span of the columns of A is all of Rm, right? If you take a linear combination of the columns of A, you can make any vector you want in Rm space. Okay? So all of these are saying that. And A has a pivot in every row. Okay? If those 3 things are true, and they're just slightly different ways of saying the exact same thing, that only happens if A has a pivot in every row. A being the coefficient matrix, not the augmented matrix. All right, we're still doing demo. This is a long one. Okay. All right, I've got a matrix A. Okay. The question, do the columns of A span R what space, is only sensible when what number is in the box?
Is this augmented? Is this matrix augmented or is this coefficient?
This is a coefficient matrix.
4.
Nope.
No?
No.
You said, the answer's 3.
3.
I said 3 first.
Yeah, I didn't answer you. I was waiting for other people to answer. I didn't tell you you were wrong. Why 3? Okay. So if I'm talking about the columns of A spanning, the span of the columns of A, right? The span of some stuff means the set of all linear combinations of that stuff, right? So I'm going to take linear combinations of the columns, right? Any linear combination of those 4 columns, I mean, just throw some weights on those vectors, add them together. What kind of vector are you going to get out? You're going to get a vector in R3, right? So when I ask, do the columns of A span something, the only thing that makes sense is R3. I'm asking you, can you get every possible vector in R3 by taking a linear combination of those columns? Okay. So I want to express this question using the first bullet from before. So the first bullet said, the matrix equation AX equals B has a solution for all B's. Okay. So does 1, 2, 0, 1, 2, 0, 1, 3, negative 1, 0, 0, 1. What has to go in here? It's my X vector. It's my vector of unknowns. I have to go up to X4 because I have 4 columns, right? So I need to have 4 weights to be able to multiply them. So I have to go X1, X2, X3, X4 equal B. B is a vector. How many entries is it going to have? It's going to be 3 by 1. Yeah. Right. So think about what you're doing. So you're going to take each column of the matrix, put one of the weights from the vector on it, and add them all together, right? So you're going to end up with a 3 by 1 matrix. That's what you told me up here, right? You get things that you get 3 by 1 vectors by taking linear combinations of the columns. So here I'm going to get B1, B2, B3. Does this equation have a solution for every vector B that looks like B1, B2, B3? No matter what you choose for B1, B2, B3, can you find a solution to that equation? That is a symbol that means for every. Mathematical symbol that means for every or for all. Yep. All right, so now I'm going to express the same question using the second bullet. Right, so the second bullet, oops, go back. The second bullet was every column vector B can be expressed as a linear combination of the columns in A. Every column vector B can be expressed as a linear combination of the columns of A. So I'm going to take a linear combination of the columns of A. That means put some weights on them, add them together. Right? So I'm going to have 1, 2, 0, throw a weight on it. Oops. Can't keep writing 1, 2, 0. 1, 3, negative 1, x3 plus 0, 0, 1, x4. Can I get any B1, B2, B3? Right, given some vector B, can I create it by taking a linear combination of the columns of A? This is the vector equation that's equivalent to the matrix equation. All right, how do I answer this question? I've asked this question 3 different ways now. Row reduce, the augmented matrix, right? So my coefficient matrix is 1, 2, 0, 1, 2, 0, 1, 3, negative 1, 0, 0, 1. Augment with the thing, with the matrix on the other side of the equal sign, which is what? B1, B2, B3. Okay. I want to row reduce this thing. If it's consistent, then I'll know the answer to all of those questions is yes. If it's consistent. If it's inconsistent, the answer to all of those questions is no. almost done. So I just need to row reduce this thing. Let's start a new page. I don't know how long this is going to take. All right, so my first goal is always to get a 1 in the upper left, check, right? Then I want to knock out everything beneath it. I want to have zeros beneath it. So what's my first move going to be? Yeah. Row 2 becomes row 2 plus -2 row 1. All right, so row 1 is going to stay exactly the same. 1, 1, 1, 0, B1. Row 3 stays exactly the same. 0, 0, -1, 1, B3. And then row 2, I'm going to do -2 row 1 and add it. So I'm going to get 0, 0, 1, 0, and then -2 B1 plus B2. No. All right, so now I have a pivot in my first column, right? I've got this one. Move to the next one. I already, the place where I'd look to have a pivot already has a 0, so there's no pivots in that one. Yep, so you're going to have a free variable. Yep. So move to the next column, and I want to have a 1 right here as my leading entry. Check. Now I want to knock out what's below it. So just going to add row 2 and row 3, and that'll be my new row 3. Say that again. Go to the third row for what? What do you mean? Okay. Okay, so here rows 1 and 2 stay the same. 1, 1, 1, 0, B1. Row 2 stays the same. 0, 0, 1, 0, -2 B1 plus B2. And then row 3 is going to get added to row 2 and replaced. So I get 0, 0, 0, 1, -2 B1 plus B2 plus B3.
Something interesting.
All right, so yeah, it's in a triangular form for sure. So can you tell at this point, is this consistent? Yeah, it's consistent. Is there a pivot in every row? Every row has a pivot, not every column. But yeah, we have a pivot in row 1, in row 2, and row 3. X2 is a free variable, yes. And when you have free variables, that means you have infinite solutions, so this is definitely consistent. Yeah. So pivot in every row actually tells us, answers the question for us right away. Like I didn't have to do this augmented part, right? Having a pivot in every row automatically means that your system is going to be consistent. Doesn't tell you what the solution is, just that it's consistent. So pivot in every row, system, consistent. Okay. If you didn't have a pivot in every row, that would mean that you have a row, once you're in RREF, once you're in row reduced echelon form, you would have a row of all zeros, which means it could be inconsistent. Could be, yeah. I actually don't think you have to do that, because if there is not a pivot in every row, because that statement, that list of 4 statements, if one of them's false, they're all false. Right, okay, so for a particular, wait, let me answer. So for a particular B, yes, you would have to do the augmented matrix and continue all the way. But the question is, can you do it for every single B? right? And if you don't have a pivot in every row, then you're going to have a row of zeros in your coefficient matrix. There will be a B that will make this inconsistent. Yeah. Right. Yeah. So this whole stuff that we did on the right here with the B's, we didn't need to do that to answer the question. You can if you want, but you didn't have to. We could have answered just by row reducing the coefficient matrix. Yes.
Do we actually get a value for B at this point?
Well, yeah, there's lots of there's infinite solutions now because because we have a free variable. So so B is something that's given at the beginning of the problem, and you have to, when you solve, you're solving for your unknowns x1, x2, x3, and x4. So you can always figure them out. Now at this point, you can always figure out what they are based on this row reduced matrix. And that's actually the next question. So let's hold that thought for 1 second. Okay. All right, so my question is 1, 2, 7 a linear combination of the columns of A? Yes. Yes, because I can make any B1, B2, B3 from the columns of A based on what I did here. No matter what I choose for those 3 numbers, the system is consistent. So the answer to this is yes. I don't have to do any more work, right? Unless I asked, what are the weights, right? If you were going to write, if the answer is yes, so on your quiz, I believe I did this. I asked, is this vector a linear combination of the columns of A? If no, explain why not. If yes, express it as a linear combination of the columns of A. So you have to throw the weights on. Okay. Yeah. Yep. Exactly. This would be your vector B.
So how will we know what the weights are?
Well, B1, so B1 is 1, B2 is 2, and B3 is 7, right? Okay, so I know that x4 is -2 B1 plus B2 plus B3. So that's 9, that's 5. So your weight on column 4 is 5. That's your x4. All right, and then x3, right, from this pivot, that's x3, is -2 times B1 plus B2, which is 0. So my x3 unknown is 0. X2 is free, so you can choose whatever you want for x2. And then x1 plus x2 plus x3 has to equal b1. So x1 has to equal 1. x3 I already know is 0, right? So put a 0 there. And I have to choose an x2, and I can calculate an x1. So if I make x2 0, say 0, right? Then x1 is 1. For that, so a set of weights you could use would be 1, 0, 0, and 5. Let's make sure it works, right? So 1, 2, 7. I want to make sure I can write that as a linear combination of the columns of A. Let me copy A again here. All right, so there's A, and my weights I said are 1, 0, 0, and 1, 5. Yeah. Okay, so let's put those weights on those columns and see if we actually get 1, 2, 7, right? So I have 1, 2, 0 times 1 plus 1, 2, 0 times 0 plus 1, 3, negative 1 times 0 plus 0, 0, 1 times 5. And I get 1. Yeah, sorry, I was just being lazy. So I get 1, 2. Why am I getting 1, 2, 5? The 5 is a 7? 9 minus 2 is 7, right? I don't know why I did that. Okay, so this, right, check your work. So this is actually 7, 7, so this ends up as 1, 2, 7. Right, so yes, you definitely can write 1, 2, 7 as a linear combination of the columns of A. And we just did it. There's infinite ways you can do it, right? Because one of your variables is free. We just let our free variable be 0, and we got one particular set of weights that'll work. All right, so now I think that there's a lot of notation, a lot of concepts flying around. You need to work through some stuff on your own. I will be around to help.